was not lying. I was telling the students that I have not been in Vienna yet, but I have been in Duino, which is where he died. No, this is not it. Let me see where did it go. Okay, good. So what I was saying is that now we are practically in a position to see where the laws of thermodynamics come. But just let me point here. I showed you that when energy goes flowing from the system that has the highest tau parameter to the lowest, the probability increases. Do I want it that way? Yes, because you understand, if I take a system, what is the state of the system? Like G of U initially will depend on the initial state of the system. Remember, is the sum of G of U1, G1 of U1, G2 of U2, and this sum, we said, is dominated by one term, and the system eventually will go there. So initially, where is the system? Well, that depends on how I prepare my system originally. I can take this system in any way I want. So originally, I have G1 of U1 initial times G2 of U2 initial. This is the number of states compatible with my system initially. If this one is prepared in a certain way and this one is prepared in a certain way, this will be the initial state. When I put them together, as we agreed, the probability will become any of the terms in this sum. All these terms now become accessible to the system. But, of course, I said already, it is more likely to be in the biggest of all. But you see, the biggest will be bigger than this one, obviously, because this one is one that I picked at random. So you see, what will happen is that the G of U will always be bigger than the G initial. Okay, so when you leave a system, inevitably it will end up being in a state of higher probability. So this thing that I showed is consistent here, that the probability increases when the system that has the higher temperature sends energy to the lower temperature, is what will happen, because the system has to go always to states of bigger probability. And that's what I am observing. And so what it is true is the following, that even if I prepare my system in such a way initially, it is very far from equilibrium. As I told, I put a part that is initially very hot. Maybe I do a little bit of math of that. I thought I had done, I have done it here for a real system. Yeah, let me give you a real system, and I believe this is an example in the book of Kittel. I don't know. It's picking two pieces of, what does it pick? Copper. 2 pieces of 10 grams of copper, okay? And one is cold, or I would say room temperature, 290 Kelvin, and this is hot, 350 Kelvin, which corresponds to, hot but not boiling, yeah? So, and let's say you keep them separate. So, and then you put them together. What is the change in am I convinced that the entropy increases when I put them together? Well, we know from thermodynamics what happens. If you put these two systems, and let's imagine that they are identical, that's why I chose 10 grams of copper here and 10 grams of copper here. When I put them together, you know what will happen. Temperature will flow, energy will flow until they equilibrate the temperature. So how much energy will be given by this one will be CV times the final temperature minus 290. That's the one that gains energy, okay? How much energy does the other lose? times TF minus 350. Okay, that's how much CV is the amount of energy per degree. So we are going to do thermodynamics later very carefully, but just to do a rough calculation the way you did it in physics 3. This is the amount of energy lost by one, this is the amount of energy gained by the other, they have to be equal, so from that, that's called the first law of thermodynamics. From that equation, you can find the final temperature. And it wouldn't surprise you that if these two things will be equal, TF minus 290 has to be equal to 350 minus TF. Magnitude, these two numbers have to be equal, so that means that TF is 290 plus 350 over 2 or 320. So that part is the easy part. You put two identical systems, the temperature final will be halfway. Okay, so now one loses energy and gets colder, goes from 350 to 320. The other gains energy, goes from 320 to 290. How much energy, by the way, flows there? Well, let me calculate. CV happens to be 3.389 joules per gram per degree. That's an experimental information that chemists will tell me. I multiply this by 10 grams and I multiply by 30 degrees, which is the delta T. So CV delta T gives me the amount of energy that we exchange. 30 degrees. So this is 3.89 times 30 is 117, is that correct? This is 3.89 times 10 is 38, 117 joules. Okay, gram, kilogram, Kelvin. So this is the number of joules. Why did I write 11.7? I don't know. Doesn't matter. This is the amount of energy one loses, the other gains. Why am I telling you all this? Because let me try to estimate what will happen when they exchange this energy. And one is sending a little bit of energy to the other. It's quite difficult, and we will learn later how to evaluate the exact change in entropy when the system's cool. That will come in the part of thermodynamics of the course. But let me make a very crude approximation. Let's imagine when they exchange how much the first 0.1 of a joule of energy. So I put them together, and eventually 117 joules will be going from one to the other. Let me consider the first 0.1, just the first little bit of energy that goes from the hot one to the cold one, okay? Why do I want this little piece? Because I assume that when this little amount of energy goes, still there will be not that much change in the temperature, right? You have to send 100 joules to change. So if I send 0.1, practically I can consider that delta S over delta U, the change in temperature, the change in entropy over the change in energy, which is 1 over T. We agree that that's what 1 over T is. The T will not have changed too much. In that way, I can calculate the delta S. The delta S will be delta U over T. Okay, because if only 1 part in 1,000 of all the energy has to flow, it didn't have time to actually heat up yet. So if this amount changes, let me consider how much does the entropy of the body that is giving up the energy, the hot body, the one that is giving up the energy. The delta U is minus 0.1 joules. The temperature didn't change yet, it's 350 Kelvin. So the delta S, the diminishing in the entropy of this one will be that number, minus 0.1 over 350 that I wrote here is minus 2.86 times 10 to the minus 4 joules per Kelvin. Okay? Entropy, remember I told you, in the real units is energy per degree. What about the other one, the one that gains entropy? For this one, delta S is plus 0.1 joules. So I'm doing a very crude estimate. We are going to learn how to calculate these things really in thermodynamics, but just a crude estimate. This is how much it gains. The temperature was 290 Kelvin. This one doesn't go that much different by getting just this little amount of energy. So the change will be this number, which is 3.45 times 10 to the minus 4 joule per Kelvin. Okay? So this is how much one loses, this is how much this gains. The total change, as you see, is positive because this one gains more and this one loses. If you combine those two numbers, delta S1 plus delta S2, you get 0.6 times 10 to the minus 4 joule per Kelvin. So when this little energy flows, the entropy increases in my system. One loses a little bit of entropy, but the other gains more entropy than this loses. The total change is this amount. Okay? So the sigma, the delta sigma, remember this was a K sigma, is what we call the actual entropy. So the delta sigma is the delta S over the Boltzmann constant. So it's 0.6 times 10 to the minus 4 joules per Kelvin divided the Boltzmann constant. I know that we didn't discuss where does it come from, but let me take it for granted. It's 1.38 times 10 to the minus 23 joules per Kelvin. So this is a number, and the number is 0.4 times 10 to the 19. So this is the change in the logarithm of the number of states when first a little bit of energy is exchanged, which means that the number of states that the system will now have access to compared to the number it had before will increase by e to the, because this is the logarithm of the number of states, this is sigma, is e to the 0.4 times 10 to the 19. So this is by how much the probability of the system will increase if just the first 1,000th of the energy they are going to exchange is exchanged. So that tells you why it is that always energy will be leaving the hot system and going to the cold system, because look by how much the probability of the system increases. How much more likely this is that going the other way around, that the hot system gains a little bit of energy and the cold system loses a little bit. It can happen because molecules can flow in any direction. And when they collide, they can transfer energy in any direction. But this is the likelihood that it will go in the direction that we call the right direction, from hot to cold. Okay? So this was a way of making this more realistic to you.
Is this compared to staying the same, or?
Yeah, to staying the same. They staying the same. This is probably staying the same, but it will be probably another factor like that if I calculate going in the opposite direction. So now let me try to see well, let me just motivate one more example so that you will see that I'm not cheating when we say that probability goes in the, oops, health part. I don't know what I did. What is this? So move it one page. Okay, so let me just one more simple calculation, and then we'll try to actually generalize all this. And the simple calculation is the example I gave you before. The probability that all the molecules of oxygen in this room are in one half, as opposed to the probability that they are in both sides. In one case, it's 1/2 to the n, the likelihood of this happening. In the other case, is combinatorial n/2, again divided 2 to the n, because this is the probability of each state, and there was one way of all the molecules being in one half, and there is this many ways of having them split 50-50. Okay? So, if that is the case, and did I do the numbers here? Yeah, I did it. Okay. So, if I want to calculate the change in entropy when all the molecules mix up, I have to calculate the logarithm of this minus the logarithm of this. Okay? The logarithm of this will give me the entropy of this state, the logarithm of this will give me the entropy. So it's ln of combinatorial n/2 minus ln 1. Okay? I will have to do minus the ln of 2 to the n, but here also minus the ln of 2 to the n, so those cancel if you want. What matters is that this is this many times more likely. So the delta sigma is this number. Okay? The change in entropy when the molecules, instead of staying all in one half, mix up. This is the increase in entropy. And, well, let me think. Log of 1 is 0, of course, that is easy. And this log is the log of n factorial over n/2 factorial squared. Okay? And so let me use very quickly the Stirling approximation to get that number right. This one is n plus 1/2 ln n minus n minus square root of 2 pi. Actually, I don't need it, but if you want, let me leave it for completeness. And I have to subtract minus n/2 plus 1/2 ln n/2, but I have to put a factor 2 because I have it from here and from here, so I have 2 logarithms, minus plus, sorry, n/2 plus n/2 plus twice square root of 2 pi. Okay? This comes from applying the Stirling approximation in the numerator. This is in the denominator. I put it downstairs. It's not that it's divided. I just put it next to it. Okay? But because I have a square, I have a factor 2 here. And here I have not just n/2, but I have twice n/2. So this and this cancel. So what matters is that I have n plus 1/2 ln n minus n plus 1 ln n/2. Okay, put this 2 here, and I have the 2 square root of pi, that number. I don't want to keep it because you will see immediately that it's totally irrelevant. So, and this is ln n minus ln 2. So this is n plus 1/2 ln n minus n plus 1 ln n. So this is minus 1/2 ln n plus n plus 1 ln 2. I separated this as ln n minus ln 2. So the term ln 2 appears here, and this one gives me that. And you see here where the story is. This number is 10 to the 22. It's n or n plus 1 times ln 2, which is 0.7 or something like that. So this is of the order of 10 to the 22. This number is the ln of 10 to the 22, which is 22. So this number will be 10, 20, 30. So what matters is this, it's 10 to the 22. So the increase in entropy when the molecules, instead of staying all in one half, mixes is of order 10 to the 22. So no wonder that if you open the communication between the two halves, the system will be in a state when all the particles are equally distributed and you don't die. So the fact that the possibility of you not dying is 10 to the 22 times bigger than the possibility of you dying. So that's why you don't die. Not because it's impossible, because it's very unlikely. Okay? Not impossible. Absolutely not impossible. Listen, all the molecules can do what they want. I mean, think it. A molecule can be here or there, can be next to your nose or to mine, and each molecule chooses that. If all of them happen to be here, it's your loss, and vice versa.
There's still rules in terms of like forces from molecules and molecules.
Say it again?
There's still rules between the forces between the
No,
molecules themselves.
no. That's the point. The model of an idea of the gas in these rooms are molecules moving at random. They barely interact. And we will do that. We will calculate the distribution, you see, they barely interact. They are as likely to be, the fact that they are distributed is part of statistics. It's not a problem with any distribution that they repel each other. No, no, and no, and no. It's because they are more likely to be equally distributed than not. There is no repulsion between them. Because even if they all concentrated here, we will do the calculation later, you will see the distance between them is hundreds of times bigger than the size of the molecule. So it's not a repulsion. I mean, if you concentrate it all in that little corner, yes, you might find that they start repelling each other. That means that you are transforming the gas in a solid. But we are not there. Just diminishing an ideal gas to half its volume, still they don't interact. So it's just the laws of statistics. No, don't rely on some forces. You are saved only by statistics. Okay, good. So now I am in a position to try to see if I can establish why is it doing that? But please help me. Okay, go back. No, go forward. Okay, now I can establish the laws of thermodynamics the way you learned it in elementary from the things we said. So what did you learn in elementary thermodynamics? First, what they call the zeroth law of thermodynamics, which was a sort of an afterthought. The laws of thermodynamics were established in 1830, but at some point in the 1930s, when they try to make it nice, they say, well, there has to be a basic principle in thermodynamics that says that if system A is in equilibrium with system B, and system C is also in equilibrium with system B, B and C are in equilibrium between themselves. It's sort of an obvious afterthought, but it is true. I mean, that's the idea. We say if T1 is equal to T2 and T2 is equal to T3, T1 and T3 are equal and the two systems will be in equilibrium. Well, that is simply saying that if the ln of G1 derivative respect to U1 is equal to the derivative of ln of G2 respect to U2, and also the derivative of the ln of G3 with respect to U3 is equal to the derivative of ln of G2 respect to U2, if those two things are equal, this is equal to that. Well, it's not such a big surprise, right? So, because we said that this is all we need for the system not to exchange any more heat and be in equilibrium. So, it follows that if two systems will be in equilibrium with the third system, they will be in equilibrium with each other. So, that sort of follows. This is, if you want, the zeroth law of thermodynamics. The first law of thermodynamics, what does it say? Of course, there are many more things to say. Say that energy is conserved, and when you put two systems in contact, if one loses energy, the other gains. Well, we have been using that as our basis. We are assuming that there are such things in the world, that a system that is isolated and can only, different parts can have energy, but nothing go away. So saying the first law of thermodynamics is essentially an obvious thing. We are saying simply that when two systems are in contact, if we say that no energy is flowing, no energy is flowing. Whatever one loses, the other gains. So here we don't even have to say. The second law of thermodynamics is a little more interesting. But all it's saying is what I said here. Let me make it more plausible with the picture. That if you have a system that you prepare it in some initial condition, G1 of U1 initial, G2 of U2 initial, this is the probability at the beginning. When you put them in contact, energy will flow in such a way that one will gain energy, the other will lose energy, but in such a way that entropy will be increasing. So if these are the energy, this is U, one might do something like this is U1 and this is U2, and these curves have to be symmetric because what one gains, the other loses. But while this is happening, if you write here the logarithm of G will be increasing somehow. This process will always go in the direction of increasing this. Why? Because if this is the initial, when you put them in contact, of all now you are making available all possible values of U1 and U minus U1, but of all these terms, the system will overwhelmingly go to the biggest term in the sum, and the biggest term in the sum, as by definition, is bigger than any other term in the sum. So we get that ln of G, eventually G of equilibrium, which is the, if you want, the G1 of the U maximum times the G2 of U minus U maximum is always bigger than this one, okay? So when you put them in contact, the system will always increase the G's, which means that it will always increase the ln G, and that's what we call entropy. So that entropy increases is nothing else than saying that it's more likely to find the system wherever it is more likely to be, which in those terms seems like a tautology. So this is G1 of U1 initial, G2 of U2 initial. So you see, the second law of thermodynamics is in some sense a consequence of the way we are defining probabilities. You know, we could say something about the third law of thermodynamics. That I want to postpone a little bit, and depending on how much we go to quantum mechanics, that's something that came much later. Remember, the ideas of thermodynamics precede any idea of atoms and anything, and certainly any idea of the quantum world. But around 1920, Nernst formulated the third law of thermodynamics, and we will see some hint of them in several calculations that we'll do here, that says that when the temperature of a system goes to zero, the entropy goes to some constant limit. Okay, that's his statement. There is a lot to be said there, but it sounds sort of reasonable that of all the states accessible to the system, when you go to the minimum possible energy, there will be less of them. So in some sense, if you want to establish it, you would be saying that when the parameter tau that we define goes to zero, sigma goes to a constant. That's sort of equivalent to what Nernst said. So I would prefer not to go too much into the details of the third law of thermodynamics. We need to develop more of a feeling of how thermodynamics works in quantum world. There are exceptions to that. Not all the systems go to just one state when you go to the minimum of energy, which is this. There are systems that have, like glasses, that have many possible states. These are called frustrated systems, in which even in the lowest energy state there are many possibilities, and if there are many possibilities, sigma, G is a big number, and ln G, or the entropy, doesn't go to zero or to some trivial constant. But in general, so to speak, we will see that most thermodynamic functions go to zero in the limit of zero temperature, which are connected to the entropy. So we will come to that. Let me leave that one a little bit behind.
Professor, is that anything to do with the fermion behavior?
Yeah, this is connected to the behavior, and we will see that when we consider real systems, one consequence is that in real quantum systems, the specific heat of a system goes to zero and zero temperature, which was not the case in classical physics. So we will get examples of that soon enough, or at some point in the course. So let me skip that one for a little while. But I wanted to finish a little bit just by pointing one important thing. I said that it was not just a coincidence that we chose, instead of defining entropy, instead of defining it as the number of states, to pick the logarithm of the number of states. And there is a very good reason to do that, because which is connected to the following. Again. So what is happening here? It's out of credit. It's okay. Here it's okay. Go to the next page. So which is connected to the following, and let me point that. I didn't discuss yet too much what do we mean by saying that the energy of a system is a fixed number. You see, when what you have is a little ball, you can say, well, it's moving at 3 meters per second, so the energy is 1/2 mv squared. But when you have 10 to the 22 of them, what do you mean? The energy of each spin is an extremely small number, okay? Those of you who took a course in quantum, the energy of the spin up or down is the Bohr magneton approximately, so it's 10 to the minus 18 joules or something like that. So when I say that the energy of a system is fixed, what do I mean? I don't measure the energy of a system with 18 significant digits. Okay? I might say that the energy is 7, and I can say that I measure it with a precision of 10 to the minus 5, 10 to the minus 7, whatever, not 10 to the minus 18. So in reality, when I am saying that a system has energy U, what I am saying is that the energy is between U and U plus delta U, where delta U is a small number, that the energy of my system, U of my system, is some number in between here. That's what I am saying in reality, where this is the precision with which I can do any measurement. And so many of my definitions would depend apparently critically on this, when I say that the system doesn't exchange energy. And I want to show you why using a logarithm sort of solves this problem. You see, if you want to say what is delta U, those of you who know quantum mechanics, delta U times delta T will be h bar, will be connected to the time it takes me to measure the energy. So, but there will be always limits. Delta U will never be 0. Might be the precision of my instrument, might even be a quantum limit, but there will always be a certain delta U, because I don't take infinite time to take any measurement. So there will be a real delta U in my system, with which I have to deal with. So how does that affect my formulation of these statistical ideas? Well, let me give you one approximation to that. So let me define a quantity that in solid state appears all the time, but here it's sort of useful, which we call the density of states. The number of states in a certain range of energy. That sometimes people denote by D of U. D of U is number of states, microscopic states, per joule, or per millijoule, or per microjoule, or whatever you are measuring, okay? So the number of states between U and U plus delta U is this times delta U. Okay, my real G of U, the one I need to build my statistical models, is the number of states per unit energy multiplied by the precision with which I am measuring or defining the energy in my system, okay? So on this quantity, I need to build my statistics, okay? So That means that if I define my sigma of u as a logarithm, then this is this number will be the logarithm of this, which will be the logarithm of my d of u plus the logarithm of delta u. Okay? That's because I am using my definition of entropy as a logarithm, and you will see what is the usefulness of having that. So now let me try to think of some model with the spins I was considering. So let me see what can be d of u in our model of spins. So remember, the number of states I had was 2 to the n, and what is the range of spins? If I assume that the atomic scale, the difference between a spin up and spin down, the ball magnet or whatever, is some very microscopic number, delta, which would be 10 to the minus, I don't know how many powers in joules. So n delta will give me the total range of energy, okay? You remember that the energy can be 1, 2, 3. So this will be sort of my density of states, okay? Because it's the total number of states divided the total range, okay? So you can say that my g of u will be 2 to the n over n delta times the delta u. Okay, the g of u was the density of states times delta u. And now we can estimate what happens when I take a logarithm. So the sigma of my state, which is just the logarithm of that, is the logarithm of 2 to the n minus the ln of n coming from here plus the ln of delta u over delta. The ratio between the precision that I can obtain in measuring my energy and the atomic scale that happens to be there that I might to do something. And you see, look at this number. This number is of order 10 to the 22, right? Logarithm of 2 to the n is n ln 2, 0.7 times 10 to the 22. This number is much smaller. This number is of the order of 20, right? Because ln of 10 to the 22 is 20, ln 10, and ln 10 is 2, so 40. And so this is the interesting number that I would like to know something. So what do you want to say? That the precision with which I measure is 10 to the minus 5 joules? Okay, you are a very good experimentalist. I sort of that you can measure with the microjoule, but let's say. And this is a much smaller scale. This is 10 to the minus 18 or 10 to the minus 19. This is the microscopic scale. Okay, or minus 20, I don't know, that depends on the model. But whatever it is, this number will be 10 to the 14, 10 to the 15, something like that. If you are a better experimentalist, the number can be a little smaller, can be 10 to the 12. If you are a much better experimentalist, you might make it much smaller here, might be 10 to the minus whatever. Whatever you do when you take the logarithm, it will be what, 10. Because this is 10 to the 15, the logarithm of 10 to the 15 is 15 or 15 times 2, 30. So you see, the point is that this is the only thing that matters. This doesn't matter. So if you get a precision 1,000 times bigger, all you will change is a little bit this number. Instead of 30, it might be 50, it might be 22. Doesn't matter. Because I am using a logarithm, in any calculation of entropy, whatever precision I achieve in order to define the size of my system and the energy of my system is irrelevant to the calculation of entropy, because you see, when you have 10 to the 22, who cares if it is 10 to the 22 plus 10 or plus 100 or plus a million? Doesn't matter. So you see that the scale delta U, I buried into this logarithm. That's why it's so convenient to use logarithms, because you free yourself from the particular details of how you measured your energy or what precision is it you are using to define the energy of your system. The argument goes well beyond that. That is perhaps the biggest advantage of using logarithms. Okay, so this is as much as I want to say at this point about the microcanonical ensemble. Now I want to generalize this a little bit, and this is the great work by Boltzmann, precisely to approach getting closer to reality. And in reality, let me see if this time it behaves. Yes, it works. In reality, you never do thermodynamics of systems that are completely isolated from the world. Or, well, you never. You might want, I mean, you might be trying to apply thermodynamics to I don't know what. But in practice, you always are considering, you know, I have a glass of water here, I put it on the table. What will it do? How will it be? What will be its temperature when it reaches equilibrium? How will it move? So I want to do statistics of systems that are in contact with the environment and exchange somehow energy with the environment, okay? Later on, we'll even generalize it to systems that can exchange molecules with the environment. That's another ensemble that also Boltzmann and Gibbs calculated, which they call the grand canonical ensemble. But for the time being, I want to consider systems that can exchange heat with the environment and evolve like that, and do the statistics of that. You see, now I cannot say I will build an ensemble in which each element of the ensemble has energy E. Because if my system is in contact with the environment, energy flows in and out. And somehow, when I do statistics, I need to accept the possibility that different copies of my system will have different energies. And I need to build a different ensemble. That ensemble is called the canonical ensemble. It's an ensemble that describes a system that is what we call in contact with the reservoir and can exchange freely heat with the reservoir. So what I have in mind now is my system. I have a big reservoir, and my system is this little corner. This is my reservoir, and this is my little system. But my system is in contact and can exchange heat here. So I cannot say at any given point what is the energy of the system, because energy can be flowing from the reservoir here, from here to the reservoir. And if I want to do a statistical study of this system, I have to admit the fact that in my ensemble I will have to include copies, not all of them having the same energy. But that doesn't mean that all of them must have the same probability. Now, a system with a lot of energy is quite unlikely when this receives a lot of energy, so I need to answer what is the probability of my system being in a certain state S, and in order to compare. If in the case of the microcanonical, the answer was simple. The probability of a system being in any microscopic state were all the same, unless they had the wrong temperature, the wrong energy, in which case was 0. Now I am saying, no, any energy is possible. But let me show you what was the analysis of Boltzmann. Boltzmann said, imagine this is the system, this is the reservoir. All I'm saying is that R is much, much bigger than S. Okay? And R and S are isolated. So to the whole system, yes, I can apply the microcanonical ensemble, because this is isolated. All it can happen is that this one can give energy to this one, or the other way around, so this one can be in states of different energy. but such that the energy of the whole system is constant. So he said, well, what is the probability that my system is in a particular state in which, let's state number S. I will call it, if you want, S0. What is the probability that is in that specific microscopic state? Well, I have to count as usual all the probabilities of this one multiplied by all the probabilities of this one, right? That's the way I do it when I have two systems in contact. The probability of this one will be G of the reservoir, and let me assume that this particular state S0 has energy E sub 0, epsilon 0. Okay? Any state must have some energy. So this will be the probability of the reservoir of having energy U total minus epsilon 0 multiplied by the number of waves of this one, which I said is just one, because I'm saying this happens to be just in that state. So the total numbers of waves of that happening is this times 1. Okay? This is the total number of ways in which the system can be. This in whatever it is, and this one in the state S0. Okay? What about another state, the state S1? Let me by symmetry call this S1 with energy epsilon 1, and this S2 with energy epsilon 2. Okay? This is one certain state. And now I want to calculate what is the probability of my system being in state S2 with energy epsilon 2. I'm not saying that epsilon 2 has to be different from epsilon 1. Perhaps it's the same. Because you see, we found that there are many microscopic states that correspond to the same energy. So epsilon 2 is some other number. Can be the same, can be different from epsilon 1. Well, but this one, by the same logic, will be GR of U minus epsilon 2 times 1, okay? And what does it mean? That the probability of my state, my system being in the state 1, of my system being in state 1 over the probability of my system being in state 2, the ratio, because all I want to calculate is a ratio, then if I know that, then I can normalize, etc. Is this divided this? Is just G of the reservoir of U0 of U, the total U, which is a constant, minus epsilon 1 divided GR of U minus epsilon 2. The ratio between these two numbers will give me the relative probability of this system being in state 1 over the system being in state 2. Okay? And now let me apply to the system G what I know. This is, the G is E to the sigma of U minus epsilon 1 over E to the sigma of U minus epsilon 2. Okay? G, sigma is the logarithm of G, or G is E to the sigma. So this is E to the delta sigma. Okay? It's E to the sigma. By delta sigma, well, what I mean is the following. E of sigma of U minus epsilon 1 minus sigma of U minus epsilon 2. So if I calculate the difference in entropy between those two states, I am calculating how much more likely is my system to be in state 1 than in system 2. Until now, I am sort of walking in circles. I haven't said too much. But this is the important idea, that P of state 1 over P of state 2 is just E to the difference in entropy between of the reservoir in the two cases, delta sigma of the reservoir. Let me put an R to remind myself that I'm talking always of the reservoir. Okay? Because now is when I will try to calculate something. I will say the following, that sigma of a certain state of the reservoir, sigma of U total minus epsilon 1 is what? Because I am saying that the reservoir is so much bigger than the system 1, this total number is certainly much bigger than that. So this I will approximate by sigma of U minus the derivative of sigma with respect to U multiplied by epsilon 1. Okay? Because epsilon 1 is a very small number, so I am approximating around U. U is the total energy of my system, which is a fixed number. If you want, you can put it U0. I didn't call it U. I believe in the book they call it U0. Okay? And for the system 2, it will be pretty much the same. Sigma of U minus epsilon 2 will be sigma of U minus the sigma du multiplied by epsilon 2. Okay? So you see that when you calculate the delta sigma, this minus this cancel, and all you get is this. And the sigma du is just 1 over the temperature of the reservoir, right? The sigma du is what we call 1 over the tau of the reservoir. So the delta sigma is minus 1 over, it's 1 over minus 1 over tau times epsilon 1 minus epsilon 2. The difference in energy between the two states of my system. That's what? E to that is the probability of state 1 over the probability of state 2. E to the delta sigma, so E to that. So there you have it. That's the big result that actually Boltzmann wrote. That this is E to the minus epsilon 1 over tau over E to the minus epsilon 2.
Right.
Where tau is the temperature of the reservoir. Okay? So he said, if the two states happen to have the same energy, as you see, they are equally likely. But if one state has more energy than the other, well, the relative probability will depend on that. This factor that appears here is what is called the Boltzmann factor. So actually, of the many contributions of Boltzmann, besides the K log P, this is probably the ones that mostly quoted. The Boltzmann factor, to decide with what probability do I consider that my system is in a given state. And he said, well, with probability equal to E to the minus the energy of the state over the temperature of the system, of the bath or the reservoir with which it is interacting. Okay? So far, I have to transform this into a probability and something with which I can do calculations. And that will be the job that I will just start today, but that we will do next time. But you see, that's what we are saying. The probability of my system being in a given state will be proportional to E to the minus energy of that state divided tau. So states with the same energy have the same probability, but states with different energy now will appear with different probabilities. So when I do my ensemble, now I put many copies of the system, but I don't put them all with equal probability, as I was doing before. I put them with this probability. So I pick every possible state of the system, but if a system has energy epsilon 3, the probability with which I put that in my system is E to the minus epsilon 3 over tau. So of course that means that I would have to normalize, because if I sum over all the states, the probability of P sub I, when I sum over all the possible states of my system, which is the sum over all states, is the sum of e to the minus epsilon of the state I over tau. And I have to sum not over all energies, okay, over all possible states. So if there are 5 states with energy, with a certain energy, I have to put 5 times this term in my sum. Okay, that is probably one of the biggest contributions of Boltzmann, because he gave a name to this calculation. He called it the partition function of the system, Z. Actually, in German, this is called Zustandsumme, the sum over all possible states. But that's the definition. You sum e to the minus the energy of a state over kT, sum over all states of the system. That's, if you want, is the normalization constant, because the probability of any given state has to be, the probability of state 1 has to be e to the minus epsilon 1 over kT divided z. Okay, z is the constant of normalization. So formally, it's like the constant of normalization. Now, this is a real probability, because if I sum over all states, I get 1, right? Because the sum is z. But you will see later that if you know z of a system, the objective of any problem in statistical physics, of any model you come up with, is to calculate z. Once you know z, it's just a few derivatives to calculate the temperature, the energy, the pressure, the state of the system, whatever. All the information about the system is in the function z. So the whole chokhmah of any problem is to just being able how to get z. It will not surprise you that only for the easiest models possible do we know how to calculate exactly z. Okay? In 1 dimension, we know it for almost every model you can invent. In 2 dimensions, we know it for very few models, and the first time that somebody did it for a real model, which was the Ising model, that person got the Nobel Prize out of that, which was on Sacher, Lars on Sacher. In 3 dimensions, we practically don't know how to calculate this for any model. Doesn't mean that it's hopeless. We can do many things. There are many schemes to approximate z, to estimate what are the derivatives, and there are many things you can do with the model short of actually knowing z. But your ultimate goal, if you could do what you want with your model, is to get z. So we will do it for simple systems with 2 or 3 levels of energy. That's easy, because then it's a finite sum. But in a real complicated system, z is complicated. But this is the goal, if you want, of statistical mechanics, to calculate for a given system. You know all the energy levels, you know all the possible states, and you calculate this sum. So what we will do next time is just calculate a few examples. We'll do it for the simplest system, which is what we call the 2-level system, a system that has 2 levels, 0 and epsilon, and can be either here or here. So we'll calculate the partition function for that system. And you will see that from that we can get the average energy of the system, the specific heat, everything you want once you calculate that. So that is our goal for next time, but that will take us not too long. So next time, after I finish this example of the 2-level system, I will suspend for a little bit the formal statistical mechanics, and I'll go to kinetic theory. So next time we will be heavily into kinetic theory. PV equals nRT, Boltzmann distribution of velocities, of molecules, etc. All the cute things that you learned in old days, and now you know where do they come from. Okay? Which was the first application of the ideas of statistical physics to calculate quantities in the real world. Diffusion constants, viscosities, everything that you measure in statistical systems. So I'm stopping here. but I almost finished, no, I finished the content of chapter 2 in the Kittel book. This is the beginning of chapter 3, but I will go very little into chapter 3. I will stop, and I will move to the book of Blandel. By the way, many of the things I've been saying are also discussed, and not badly, in this book as well, so you can check it here. But starting next class, once I start kinetic theory, I will follow this book in more detail.
Which book?
This one, which there are electronic copies that some of you have.